Hey guys, let's do another live problem. And hopefully my explanations are better and we do a harder problem. Okay? 81! Let's just do it, man. Let's just do it. Alright, I'm gonna have a good explanation this time. I'm gonna have clear thoughts. I'm gonna do a good job. My clock's already running. Alright, let's do it. Given the root... Can I highlight, please? Sorry, good explanation starting now. Ready? Given the root of a binary tree, collect a tree's nodes as if you were doing this. Collect all the leaf nodes, remove all the leaf nodes, repeat until the tree is empty. Okay. Some kind of like topological sort-ish type thing. Is there an order that we want to collect the leaf nodes? It appears no, based on this explanation right here. So okay. I think I have an idea. We can kind of use the topological sort idea, right? Can we just go through can we go through all the nodes in this graph, BFS probably, and we can put each node inside of like a dict, and then we can have the value be the integree of that node. And then we'll just we'll do the topological sort idea where we start with, or we remove any nodes that have integree 1 first, because those are the leaf nodes. And then whenever we do that, we need to also keep track of their parents, I think, because we know whenever we remove a node, we're removing 1 from the integree of the parent node. So we need to maintain the parent as well. So I think I can do, my parent is like this, and then I can do in degrees as a default dict. And then we can just BFS here. So we can have and then we also want to start, well, maybe I shouldn't think about that yet, but essentially my queue will look like this, and then while the queue has elements, I will get my current element, and then what I will do is we don't care about the actual integree, because integree implies, like, if you look at this node 2 here, we were looking at this edge from 2 to 1, this edge from 2 to 5, and this edge from 2 to 4. But when this node's a leaf node, it will still have this edge from 2 to 1, but we know it has no children anymore. So we really want to only track the integree based on how many children it has. So what we can do here is, if cur.left, then we can do integrees of cur plus equals 1, and then we can append cur.left to my queue, and same thing for cur.right. Integrees cur plus equals 1, queue append cur.right. And so yeah, I think that is good. Do we need the parent node? We do, right? Is there any other easy? No, I think this is fine. We can just do it like this. Okay, so we can do pair of cur dot left is equal to cur. Then we could do parent of cur dot right is equal to cur. Yeah, I think that should work. Okay, and so now what we need to do is the only thing here is like this might be kind of slow. Like, what's the most efficient way to go through all these nodes and process them now that I've collected them in my n degrees? I suppose I could do like a BFS again, pretty much. Maintaining like the topological sort idea. So this would be node per node in degrees if in degree. So actually this is, so we want all the nodes with a 0 in degree. So interesting. So we actually want like a set. Are these nodes like labeled from 1 to n or something? I think not necessarily. So I'm not loving this, but what we can do is we can add each node to our set. Do we only care about the value? Yeah, but we should add the nodes to our set. So okay, and so now what we can do here is node for node in nodes if node is not in degrees. So this would mean that the node has in degrees 0. So we want to process it first in our queue. So we'll have a result. This is probably overkill for a problem with acceptance rate of 81. Anyways, so while my queue, so we want to do like a level by level BFS now. So we'll do level, it's like this, process all of the nodes in this level. We'll get cur is equal to q top left. We want to level dot append level dot append cur. And so since we're removing this node, which is a leaf node, we want to subtract the in degree of its parent. So we'll get the in degrees. It might be easier to just go like parent is parent of cur, and so we'll do in degrees parent minus equals 1 if in degrees parent is 0. Then we'll put the parent onto our queue. And then once this level is done, we want to append this to our result. So I feel like this is probably overkill. Key error. Oh, the parent of root is none. we'll do parent of root is none, and then parent equals parent of cur. You know what? We don't even have to bother with this. I could just check here if cur is the root. I think we can continue, but yeah. Type error. Oh, right, because I have to append the value here. So is this really what they're looking for? Depth first serve. Can I just send this to the DFS? Maybe I may have overcomplicated it. Video solution.
Hello everyone.
This is like, can you imagine in the video for this problem? I start watching a video for the problem. Approach 1, DFS with sorting. The order in which elements will be collected depends on the height of those nodes. The height. That's sorting. Before I look at this, let me just think of what the complexity of my solution would be. Well, I'm BFSing through the entire graph, so it's just O of n, where n's number of nodes. And then here I just BFS through the entire graph one more time, so this is just O of n, and then my space complexity is also O of n. So, what's the complexity here? N log n, we don't like that. I don't like that. Depth first search without sorting. Topological sort to resolve it. Hey man, I got the Google offer. Maybe I'll take this solution, I guess. But okay, let's read their DFS solution without sorting. Soon approach one, there's an additional sorting that is being performed, which increases the overtime. The question we can ask you to do better than this answer. This will try to remove the sorting by directly placing all values in their respective positions instead of using pairs array to collect all the height val pairs and then sorting based on their heights. We'll directly obtain the solution by placing val to the solution array to clearly clarify the given binary tree. 45 goes in the first position, 2 goes in the second position, 1 goes in the third position. Modifier get height method directly into the nodes into the solution array. Solution array is kept empty in the beginning. When you encounter increasing height, will keep increasing the size of the solution array to accommodate for these elements. So for solution array. What's happening here? I don't know, man. Should I try to do it this way? Okay, what are they doing here? This dot solution dot size. Okay. It's so weird to read. Okay, maybe I'm doing this myself. Find leaves. I don't know why this is so like confusing for me to read right now. All right. Well, I guess I'm getting humbled, right? This is what I was looking for. I just can't put in the effort to read the solution. Okay, come on. Get height. I mean, yeah, I understand. You're getting the height for this node, but why? What is this doing for you? Like, sure, you get the height, whatever. This dot solution is a new array list. And then all of a sudden, it's the new solution. But why? So they're using the current height. They're using the current height as like an index for their solution list. I don't understand that though, because aren't these at different heights? 3's at height 1, 4 and 5 are at height 2. So I don't really understand how that works. Alright, maybe I should actually read this first one. Oh, dude. This is such a yap fest. It's so long. I don't know if I can do it. Come on. You can power through it. Approach 1, too fast with sorting. In order, the order in which the elements will be collected and found is the height of these nodes. The height of a node is the number of edges from the node to the deepest leaf. Oh. Oh. Okay, the height's not the height from the root. The height's, you're calling the height like the distance from, you're calling the height the distance from my node to a leaf node. Alright, that makes sense. That makes sense. Okay, this makes sense. And how do they know when to like increase the size of their solution though? Yeah, I suppose that makes sense. Alright, I'm gonna try to do this. So there, this is the height. Okay, so if not node, I think I want to return 0. Are they returning -1? I don't really love that. Like, maybe I could do it like that. I mean, I understand. Yeah. No, actually, that kind of makes sense for this problem. Right, so if the node doesn't exist, we'll return -1. Otherwise, left would be 1 plus DFS node dot left, and then right would be 1 plus DFS node dot right, and then so the height is going to be the max of left right. And what they're doing is, yeah, so if my height Yeah, if my height is equal to the length of the result, then res.append another list, and then res height. Well, actually, I don't have to do it here, but and then I need to return the height here, don't I? DFS on the root here. Return res. Yeah, this makes sense. I was getting confused why or how they know like I was getting confused like when you add a new list to my result, right? So we're never accessing some kind of height that's out of bounds. But it makes sense because you have to dig all the way down. And once you dig all the way down, the first height you're going to be processing is 0 because DFS will dig all the way down to the actual leaf nodes from the root graph. And then this will process the nodes with height 0 first. And we know that like this length of result is currently a height of 0, so we can use this little rule here where if the height is 0, length of result is 0, that means, you know, we're going to be out of bounds. So we need to add another list here so we can index at 0. And then for the next iteration, or maybe not the next, well, yeah, for the, well, no, but essentially when we get to height 1, we'll process height 1 next, right? You're going to process height 0, then height 1, then height 2, then height 3, and so on. So when we process height 1, at that point, we will have one list inside our result array. So the length of res will be 1, and the height will be 1, and we can use this rule again to append a new list. So, yeah, I had a little trouble envisioning that, but it makes sense now. And this is a lot shorter than my topological sort solution. So, yeah, cool. 3 milliseconds.